Hello, hi guys. Welcome to my channel. So today I'm going to take you through a series of lessons which will be covering linear algebra course, as it is provided mostly in many universities. What is going to happen now is that this lesson is going to be an introduction to the subject, where we are going to cover only the preliminary content that we need to know before we go deeper into the whole subject of linear algebra. You see that? So to begin, the first thing that we're going to do is we'll try to come up with some sort of an informal definition as to what exactly is linear algebra, or to just get a brief idea of what this subject is all about. You see, then from there we're going to talk about all the preliminary work that at least you have to build as your foundation to this course. You see, so yeah, let's go. So first, what exactly is linear algebra? You see that? So to me, linear algebra is defined as an abstract theory of matrices. You see that? So the way I define linear algebra is that linear algebra is more like an abstract theory of matrices. You see that? So I think everyone is well aware at this point in time, or what do we mean by the term abstract, especially when it comes to math at this level. So I won't go into the details of that, you see. But linear algebra, if you are to define it, one way of defining it is that it is an abstract theory of matrices. And the reason why I say so is because what you're going to see is that all the different chapters that you're going to be covering, they will be having something to do with matrices. So that's why I've chosen to define linear algebra this way. But many different authors, they also have a different way of putting down the definition of linear algebra. It's all based on how each individual views the subject. You see that? So the definition at the end of the day doesn't matter. What matters is for you to understand the main content that is going to be covered in this subject. You see that? So just as I've left out already that this has something to do with matrices, it means now before we move forward to start looking at the details of this course or this subject, it will be good for us to do a brief revision of matrices, so that at least we have all the foundational tools that we'll need, you see. So what we're going to do now is we are going to then take this time to introduce matrices and then go through all this basic theory at a very fast pace. So now, matrices. So what are matrices? You see, so matrices, so far we know that matrices are mathematical objects that are made up of an array of numbers as rows and columns. You see that? So everyone, I think, at this point in time has an idea of what a matrix really is. So informally, this is how we define a matrix. It is just a mathematical object which consists of numbers which are written in the form of rows and columns within that object, you see. So examples of such objects are as follows. So examples of what we call matrices is something like this: 2, 3, 4, 5, 2 minus 1, 7. These are all different examples of matrices. You see that? Yeah, there are many different ways or different examples that one can put down But one thing that characterizes these objects that we refer to as matrices is that every time when you come across one, it always consists of an array of numbers into rows and columns. Like, for example, if you look at this first one, you can see that we have an array which goes horizontally like this. These are what we refer to as the rows. You see that? So when you take all these arrays horizontal like that, we refer to these as the rows of matrices, like that. You see. Then again, within the same block again, you will see that you also have numbers which are arrays which are vertical, as you can see, like that. So these vertical arrays that you see here are what we refer to as the columns of a matrix, like that. So every time when we encounter objects like these are what we refer to as matrices. You see that? So one thing about them is that one thing that characterizes them is the columns and the rows, and also the numbers that fill up all those columns and rows. So the individual numbers that are found within certain rows or columns, like for example this number 3 sitting there, we refer to these as the entries of a matrix. You see that? So all these things, we refer to them as the entries of a matrix, like that, or you can just say terms. But yeah, the most common term that is used for that is that we refer to each individual number as an entry of the matrix. You see? So all this that we're discussing, yes, it's basic stuff, but we first have to make sure that we get the language right before we go on to start talking about things that are much deeper in this subject. You see that? So now we now see what we mean by an arrangement of numbers into rows and columns, and all this being written within brackets, as we can see there, like that. Then the other thing that you should know is that when it comes to matrices, there is something which is called the concept of order. You see that? So there is something that is called the order of a matrix. This is very important also for you to make sure that you really understand it. You see that? So a matrix that has n rows and m columns is usually referred to as n by m matrix. You see that? So one thing that you should know is that not all matrices have the same number of rows and columns. You see that? Some can have a certain number of rows, some can have a certain number of columns. You see that? So the number of rows and number of columns that a particular matrix has is called the order of that matrix. So a matrix that has n rows and m columns is usually referred to as an n by m matrix. You see that? So this n by m is called the order of the matrix. You see that? So this thing which is more like a product, which is not necessarily a product, which kind of give us an idea of how many rows and how many columns does a particular matrix have, we refer to that as the order of that matrix. You see that? So which means for example, if let's say you have a matrix such as this one, 3, 4, 3, 2, 1, 7, then this matrix that is we have here is called a 3 by 2 matrix. You see that? So this 3 by 2 thing that we have written here is what we refer to as the order of the matrix. You see that? So which means if someone were to ask you what is the order of this matrix, you will simply say that the order of this matrix is 3 by 2, where the number of rows is always written first and the number of columns is written last. So let me put that also as a comment so that you don't get too opposed, because that's some convention that we must strictly restrict to ourselves to. So the first number specifies the number of rows, and then the second number that we have here specifies the number of columns. You see that? So this thing is what we refer to as the order of a matrix. So it is very good that if you are to start looking at matrices at this advanced level, that you understand all the terminology that is associated with matrices, and to also understand the things that you can do with these objects. You see? Okay, so now we have given a definition of what a matrix is, and we have also understood the concept of order. Then the next thing that we would like to discuss now is to start looking at some special types of matrices that also you must make sure that you are aware of, as they are always brought about linear algebra in different situations. So let's look at some special matrices that you should know in this subject. So we have many different special matrices that we are going to discuss, but so far there is a certain set which we call the fundamental set, or the fundamental foundational set of matrices that one has to make sure they at least have an idea about them. You see that when you are to start studying these subjects. So what we're going to do now is we're going to lay down all those different types of matrices. So the first matrix in the list which we want to talk about is what we call a zero matrix. You see, so we have this matrix that is called a zero matrix. So what is a zero matrix? So a zero matrix is a matrix which is such that all its entries are zero. You see that? So it is that matrix which is such that all of its entries are equal to zero. So an example of such is 0, 0, 0. This is a 1, 0, 0, 0, 0. So 0, 0, 0, 0, 0, 0, 0, 0, 0, so forth and so forth. So there are many different types of them coming up in different number of columns and rows. But an example of what we call a zero matrix is what you are seeing there. You see that? So this is also a very special matrix. Now you will not understand why exactly do we refer to this one as a special matrix, but you shall start to get a clue when we start looking at a particular section which talks about something called vector spaces in linear algebra. So for now, just take them as matrices that you should know, but you will then see their importance as we move forward with the subject. You see. Now that we know of a zero matrix, now the next thing that we want to talk about is a square matrix. You see that? So square matrices, there are some of the special matrices that we usually work with quite often, and therefore it's good to give a formal definition of what exactly is a square matrix. You see that? So a square matrix is a matrix which is such that the number of columns, the number of rows and columns is the same, i.e., or it's a matrix whose order is n by n, such that n is an element of natural numbers. You see that? So we have also these special matrices that we call square matrices, and the reason why they are called square matrices is actually taken from our understanding of the square itself. So we know that from geometry, a square is that quadrilateral, which is such that all of its sides are equally the same. You see that? So square matrices are matrices also that have that kind of attribute. You see that? But now, since there is no concept of length when it comes to matrices, we actually bring forward the number of columns and the number of rows to actually play that certain role. You see that? So when these two are identical, the number of rows being equal to the number of columns, then we call such a matrix a square matrix. So examples of such matrices are as follows. So 2, 3, minus 1, 0 is an example of a square matrix, and 3, 4, 3, minus 1, 0, 2, 5, 2, 7 is another example of a square matrix. You see that? So we need the number of rows and the number of columns to be the same for something to be to qualify to be called a square matrix, like that. Okay, so now we are well aware of square matrices. Now, having square matrices, it now brings us to a stage where now we can also talk about this one special matrix, which is going to be very, very special. I think when it comes to special matrices, it's supposed to be at the top of this list. And this is none other than what we call the identity matrix. You see that? So what is an identity matrix? You see that? So an identity matrix is a square matrix you see that? So it is a square matrix which is such that all entries in the leading diagonal are ones and all the other entries being 0. You see that? So this is what we call an identity matrix. So an identity matrix is a matrix which is such that all the entries in the leading diagonal are ones and all the other entries are 0. You see that? But now there is a new term that has just popped up, leading diagonal. So what exactly is a leading diagonal? You see that? So to understand what exactly is a leading diagonal, let's look at the following example. Let's suppose you have this matrix, which you have here, which I will label maybe as 3, 2, 5, 0, 2, 7, 5, minus 1, 3. So this is a square matrix if you are to look at it. So since it is a square, this object actually is most of the properties that square has. So if you go back to geometry, you will know that one thing that characterizes a square is that it has two diagonals that are identical. So even this matrix also has two diagonals, which I will highlight here as follows. So there is this diagonal which goes this way, And then also there is another diagonal which goes this way, as you can see there. You see that? So this diagonal that is labeled here in blue is what we call the leading diagonal. You see that? So for every square matrix, this diagonal which is labeled or is highlighted in blue is called the leading diagonal, whilst this other one which sits here is called the trailing diagonal. You see that? So leading and trailing are terms that mostly were coined from how exactly we evaluate something called the determinant, which we are going to meet later. You see that? So, but for now, you just have to familiarize yourself with this terminology, that when we say leading diagonal, what exactly are we referring to? Or when we say trailing diagonal. So the blue diagonal is called the leading diagonal, and then the other diagonal, we call that the trailing diagonal. So you should familiarize yourself with that. Then coming back now to the identity matrix, you see that. Then what are examples of identity matrix? You see, so examples of the identity matrix are, so we have many different examples of identity matrix. So we have 1, 0, 0, 1. This is another one. So we have 1, 0, 0, 0, 1, 0, 0, 0, 1. And they go on coming with different orders and so forth and so forth and so forth, like that. You see. So these are what we refer to as the identity matrix. So it is one of the special matrices that at least you must have an idea about. You see that? So it plays a very, very critical role in linear algebra, especially when it comes to the solution of systems and many other things, which you are going to see later. You see. So for now, it's good to at least have a good understanding of this special matrix. You see that? Then now, having some knowledge about the identity matrix, let's move on to discuss more and more different examples. So now we want to look at also what we refer to as symmetric matrix. You see that? So we have also the special matrix, or these special matrices which are referred to as symmetric matrices. You see that? So what is a symmetric matrix? You see that? So a symmetric matrix is one which is such that a symmetric matrix is one which is such that non-diagonal entries reflect about the diagonal. You see that? So we have these special matrices which we refer to as symmetric matrices. So how they are defined is that these are matrices which are such that if you look at the entries which reside not on the diagonal, they seem to appear like they reflect about the diagonal. So for example, let's look at what exactly we're trying to say here. So for example, let's look at the matrix 3 minus 1, 5, then 2, 3, 7, sorry, 2, 3, 7, then 7, 3, 2. You see that? So if you come maybe, and let's highlight along this diagonal here. You see that? So you will see that if you look at these individual elements, like for example, let's look at 2. You will see that 2 is actually appearing as if it has been reflected about the diagonal line. And also if you look at 3, you will see that 3 also is occupying a distance equidistant from that diagonal line, which is the same thing which is happening also when you look closely also at 7 here. So if you look at 7 also, the same thing is happening. So every time when the non-diagonal elements, they seem to be forming their exact mirror images along the diagonal line, this is what we call a symmetric matrix. You see that? So when we talk about symmetric matrices, that's what we mean. So we don't care what is happening along the diagonal. So diagonal can have different random elements. It can all have zeros throughout. But what matters for now is that this has to be the case. You see that? Then we have also another group of matrices, almost similar to this one, but with slight differences. So we have what we call the antisymmetric matrices. So what is an antisymmetric matrices? You see that? So this is almost similar to a symmetric matrix. The difference is that when the entries reflect about the leading diagonal, their signs change. You see that? So that's what we call an antisymmetric matrix. It is almost the same structure which is similar to a symmetric matrix, but now the only difference that is there, instead of those numbers appearing to have just reflected to the other side, they seem to be reflecting and changing side when they go to the other side. So a typical example of what we call an antisymmetric matrix will be something like this. You see, so you will have 5, 3, 7, then maybe you will also have 2, -1, 4, then you will have -4, 1, -2. You see that? So if you come maybe and let's say maybe we come now and highlight here in the leading diagonal, you will see that the number 2, which we have here, seem to have reflected, but when it's reflecting this side, the sign is negative. Also, the number 1 seems to have reflected, but now the sign is positive the other side. So even 4, the sign also has changed. So the magnitude of the non-diagonal entries seems to have been kept the same, but the sign seems to have been reflecting. So every time when you have this kind of structure in which there is symmetry, but there is a lack of accurate symmetry because of sign changes, then we refer to this as an antisymmetric matrix. You see, so all these matrices, they have to be square matrices. You see that? So one thing that you must pay attention is this: NP, both symmetric and antisymmetric matrices must all be square matrices. You see that? So these are things that you must make sure you pay attention to whenever you're dealing with these type of matrices. So all these things, that's why you will see that we started talking about all these special matrices after we had laid down a definition of a square matrices, because all of them, they seem to be just all square matrices. It's very hard to have a symmetric or an antisymmetric matrix which is not a square matrix. It's impossible actually to create one, you see. So this is some of the things that you must make sure that you have an understanding of before you get deep into the subject. So to be aware of all these basics, you see that. Then we have also what we refer to as diagonal matrices. So we have also these special matrices which are referred to as diagonal matrices. These are also very special because they play a huge role in the solution of linear systems. You see that? So it's very good to at least have an idea of what we mean when we say a matrix is diagonal. You see that? So a diagonal matrix is one which is such that all non-diagonal entries are zeros. You see that? So these are matrices which are such that all elements which do not reside in the diagonal are supposed to be zeros. So examples of such matrices are 0, 0, 0, 0. So this is a diagonal matrix as well, because the main fact is, if I were to highlight here and ask the question, are all non-diagonal elements zeros? Yes, that's true. We don't care what is happening in the diagonal. So another example again will be 3 minus 1, 4, then everywhere else 0. So that's also another diagonal entry, because if you highlight here in the middle and ask yourself, is everything which is not on the diagonal 0? Yes, it's 0. So once this is the case, that all non-diagonal elements are zeros, then we refer to that as a diagonal matrix. You see. So it's very important for you to have a basic idea of all these different things that we are discussing here. You see that? Because they are going to be playing a huge role, mostly when it comes to dealing with systems, linear systems especially. You see. Then, yeah, I think now we have talked about most of the matrices which are going to play special roles in this whole subject of linear algebra. So now it's time to move on to the next thing. So the next thing that we want to talk about is the equality of matrices. You see, so now we want to talk about the equality of matrices. That's what we want to talk about now. The equality of matrices, what it means to say two matrices are equal. Do you see that? You see that? So two matrices say A and B are said to be equal if the following hold true. You see that? So now we want to understand the equality of matrices. When do we say two matrices are equal to each other? So we say two matrices A and B are equal to each other when this is the case. The order of the matrix A must equal the order of the matrix B. So once two matrices have different orders, obviously we can't talk about them as being equal things. They are completely unequal when this is the case. You see that? But this doesn't end here. So the next thing again that must be satisfied is that corresponding entries must be identical. You see that? So the other thing is that corresponding entries also must be identical. So what we mean by that, it's something like this. Let's say I have two matrices here. I have A1, A2, A3, A4. Then maybe let's say also I have P1, P2, P3, P4, like that. So if you look at these two elements here and here, we say they are corresponding entries because they all occupy the same position. If I were to ask you to describe what is the position of A1, you will say upper top left. You see that? So it's top left to say, and also B1 is also top left. So we can see that both these two elements, their positions can be described using the same set of words. That's what you mean when you say two things correspond. So if two things that correspond are identical and the order is the same, like we can see now that both this matrix is 2 by 2, and also we can see that this matrix is 2 by 2. So when this is the case, and it is also the case that A3 is equal to B3, A4 is equal to B4, A2 is equal to that, then we say these two matrices are equal. So it is very important to understand the concept of equality. It may look very trivial right now when we're just talking about it, but you will see that where it has to be applied, most people, they struggle with using just this trivial fact. So it's very good to have a good understanding of what do we mean by equality. You see that? Okay, now that we have laid down the equality of matrices, now it's time to talk about some of the most important things, especially when it comes to the discussion of matrices, which is none other than the operations of matrices. So matrix operations. So now we want to talk about what are the things that we can do with matrices. You see that? What sort of math manipulations can we do with matrices? So there are many things that one can do with matrices, but specifically for an introductory lesson, we'll just look at some of the most basic operations that one can perform with matrices. You see that? So the following operations can be performed with matrices. You see that? So there are certain operations that one can perform with matrices. And what are those operations that one can perform? So one, there is addition and subtraction. So one, it is possible to add matrices, and it is also possible to subtract matrices. We are going to see how that works. Then two, the other thing that we can do with matrices is what is called scalar multiplication, which we are going to see also how it works. Then the third operation also that we can do with matrices is the multiplication itself. You see, so these are one of the basic operations that can be done with matrices. So what we're going to do now is we'll try to take some few minutes just to discuss all these operations briefly, to understand the do's and don'ts, and also how to actually go about conducting them. So the first thing that we'll try to talk about is addition of matrices and subtraction. So how do we add together matrices and how do we subtract together matrices? You see that? So the addition or subtraction of matrices is only valid when the two matrices have the same order. You see that? So one of the things that you should know is that addition and subtraction as restrictions is not something that you can do with any two arbitrary given matrices. It can only work when the two matrices that you want to add or subtract, they have the same order. So if the order is different, then it's an invalid operation. So it cannot be performed in that case. You see that? And then the extra information that you should know is that the addition of matrices is commutative. That is, if you add together A plus B, you will get the same answer even if you say B plus A. You see that? So the addition of matrices doesn't care about the order in which you add the two matrices together. So you can put the other one first, you can shift the order, it doesn't affect the outcome of the situation. But the subtraction of matrices is not commutative. Is not commutative. So it is very important to be aware of all these things. So calculating A minus B is not the same thing as calculating B minus A. So here you must be very careful with the order in which you put the matrices together. So if they say find the difference between matrix A and matrix B, you must make sure that you write matrix A first and then B second, then you subtract. Because once you shift the order, you get a new different thing, which is not exactly what you are being asked to do. So it will be very important for you to be aware of all these things. You see that? So when adding two matrices together or subtracting two matrices together, corresponding elements in the matrix blocks add or subtract to each other. You see that? So it is very important to know exactly also how this addition or subtraction works. So whenever you're adding or subtracting two matrices, how this operation is done, it is done in an element-wise way, whereby two entries that occupy the same position, they are either added or subtracted from each other in that order. You see that? So to demonstrate exactly how this works, let's look at some example. So a typical example would be something like this. Given A, which is equals to 3, 2 minus 5, 5, 2, 7, 1, 1, 3, and also B, which is equals to 2, 4, minus 1, 0, and C, which is 3, 6, 1, 2, 2, 1, 4, 2, 9. Then the question is find, maybe the first question will be A, find A plus B, then B, find A plus C, and then C, they will say find C minus A, like that. So these are typical questions that you can get in the exam. So how do we deal with this? You see that? So let's write solutions to all these problems. So A. So if you look at A plus B is undefined in this case. Since we can see that the order of A is not equal to the order of B. So if you look at the two matrices A and B, what we have here is a 3 by 3 matrix, but what we have here is a 2 by 2 matrix, and what we have here is a 3 by 3 matrix. So since they are asking us to add a 3 by 3 and a 2 by 2, this is an invalid operation, so you cannot conduct it. You see that? Then now B, they are saying find A plus C. So since now you want A plus C, it means you just have to write down matrix A first, and then followed by C, but the order doesn't matter, remember? So we have 3, 2, negative 1. So we put 3, 2, negative 1 here. Then 5, 2, 7. 1, 1, 3. Then that side we have 3, 6, 1. 2, 2, 1. Then 4, 2, 9. Like this, you see. So now how can we deal with this? So when it comes to the addition of matrices, just as you have said, first you have to check the order. The order now is perfectly fine. It is a match. Now we just have to add them. So how does the addition work? So when it comes to the addition of matrices, this is how things work. So matrices that occupy same positions, they are added. So this is added to that. And the same thing, this is added to that. And this is added to that. So it works like that. So even when you come again, here 5 will also add to 2, while 2 will add to that 2, and 7 will add to that 1. So this is how things are going to be working as you perform this type of thing. So even here 1 again will add to this 4, and this to that, and that to that. You see, so elements that occupy corresponding positions, they add to each other. So now seeing how the addition is going to work, what is going to be our result? You see, so 3 added to 3, you get 6. 2 added to 6, you get 8. Negative 1 added to that, you get 0. 5 into 2, 7. 2, 4. Then 8. Then we have 5. Then we have 3. Then we have 12. So this gives us our final answer, which is that. So this is how you you add together different matrices. Then now C, we are asked to find C minus A. So which means you must write matrix C first, then you end with A. So since we have them nearby, let's copy them. C is just 3, 6, 1. Then 2, 2, 1. 4, 2, 9. While this A is 3, 2, negative 1. 5, 2, 7. 1, 1, 3. So once the order is perfect, now you can just do your thing. 3 minus 3 again is 0. 6 minus 2, we get 4. 1 minus 1, we get 2. 2 minus 5, get negative 3. Then 2 minus 2, we get 0. 1 minus 7, get that. 4 minus 1, we get 3. 2 minus 1 is 1. 9 minus 3, we get 6. So this is how addition and subtraction works. You see that? So these are very simple operations. Once you know the rule, how it works, everything follows just like that. You see that? But then there is something also that I forgot to add, which is also very important when it comes to addition of matrices. You see that? So let me put it as an NP here. So addition of matrices is associative. That is, if you take A plus B plus C, maybe adding A to B and then to C, it is the same thing as saying A, B plus C. You see? Which means if you're adding a chain of things, it doesn't matter in addition which two do you combine first, the result will always come out the same. You see that? But subtraction also, we can't really say it's associative, though yes, it has to be associative, because actually subtraction is also more like what we call this thing. It's more like an addition, so it also has to be associative. So addition of matrices is associative, that is, and also subtraction as well. You see that? So also subtraction, it's associative. So what we mean by that is that if you have A minus B minus C, then it's just that it's very hard to put it in a nice form. But if, let's say, maybe you deal with, because it can't work, because we'll have to pull out a negative here, because this has to be now the same thing as saying A minus B plus C. So it can't really give us the nice associativity law that we want, but its associativity, it actually follows from that of addition, because this part that we have here can be recognized as A plus minus B plus minus C. So from this we can then see that we can tell that subtraction is also more like an associative operation of matrices. You see, though I would really love to just forget about it and only talk about the associativity of addition. That every time when you're dealing with addition, this is the case. When adding 3 or 4 things, you can take any 2 at any order and deal with them, and then move on with other things like that. You see. So now we've seen how the operation of addition and subtraction work. Now it's time to move on to the next type of operation again. So the one that we're going to move to now is scalar multiplication. You see that? So scalar multiplication is an operation of the form lambda A, in which matrix A is multiplied by some real number lambda, as you can see there. You see that? So we have this operation that is called scalar multiplication, but the question is, how does it work? You see this? So in this operation, the real number alpha, multiplies all the entries inside the matrix A. You see that? So how it works is that every time when you multiply a particular matrix with some real number lambda, what happens is that real number lambda, it enters inside the matrix and it multiplies every entry of that matrix by that number. You see that? So to give a demo on how exactly this operation works, let's look at the following example. So a typical example would be something like this. given A to be the matrix 4, 2, 3, minus 1, find 3A. You see, so that can be a particular question that can be given. You are given a matrix and then they say find 3A. So that's an example of what we call a scalar multiplication. So how do we deal with that? So to deal with that, this is how we proceed. So to find 3A, this is actually saying 3 by 4, 2, 3, minus 1. So what happens is that now this number 3, it will go inside. So it will go inside and multiply everything. So it will multiply there, multiply there, multiply there, and then multiply there. So when it does that, what exactly happens as the end result? So in the end result, we'll have 12. Then at the top, when you get 6 the other side, then we get 9, then we get negative 3. So this is how scalar multiplication works. You see. So this one is no restriction, but one of the things that you should know is this result. That you should know is that if A is any matrix, then 0 by A is a zero matrix. You see that? So the zero matrix that we talked about, usually it is denoted by this big O that you see there. You see that? So big O is used mostly to represent the zero matrix. You see that? So every time when we see a big O in this subject, just know that it's always representing a zero matrix most of the time. You see that? So it will be now good also to state this line. The identity matrix, on the other hand, is represented using the letter I. So when it comes to the identity matrix, then we use the big letter I for those special matrices that we once discussed there. Like that. So it's good to keep this notation because it's more like conventional throughout this subject, and many authors, they stick to the same rules. So it will be good even for us to also stick to the same rules without changing them, like that. Okay, so now we've seen scalar multiplication, how it works, which is the easiest operation of matrices when it comes to learning all the different operations of matrices. Now we're going to move on to the last part of this lesson, which is multiplication of matrices. So that's what we're going to end with today. So let's talk about multiplication of matrices. Multiplication of matrices. You see that? So given two matrices, say A and B, we can multiply these two matrices together if the following condition holds true. You see that? So if every time when you're given two matrices, say maybe A and B, and let's say also you're asked to evaluate, let's say maybe your goal in that situation would be something like this. Let's say your goal will be to find AB, you see, written in that order, where A comes first and B comes second. So let's say you're given those two matrices and you want to find AB. So if you want to find AB, then this is what you should know. You see that? So there is some condition that has to hold true, which I'll write as C. So what is that condition? So the condition is that the number of rows of the first matrix. So every time when you want to multiply two matrices, first you must check if that multiplication is valid in the first place. And to check for the validity, you make use of this following condition. So the condition says that the number of rows of the first matrix, so how many rows the first matrix has, must equal the number of columns of the second matrix. You see that? So the number of rows of the first matrix must equal the number of columns of the second matrix. So this is how you check for the validity of the multiplication. So which means now when we talk about first matrix, here this is playing the role of the first matrix, the one that comes first, and this B plays the role of the second matrix. So that's what we mean when we say the number of rows of the first matrix must equal the number of columns of the second matrix. You see that? So the other thing that you should know also when it comes to matrix multiplication is this. So some important results. So matrix multiplication is not commutative. So what we mean by this is that the product of AB is not equal to the product of BA. You see that? But when valid for three matrices, A, B, C, this operation is associative. You see, so matrix multiplication is associative. So what it means by that is that if you say AB, then come later to say C, this is the same thing as first finding BC and multiplying with A at the end. You see, so those are some facts that you have to know when it comes to the multiplication of matrices. You see, so exactly how does it work? How does it work? So to understand how matrix multiplication works, let's look at a few examples. So let's practice this by looking at the following examples. Multiplying matrices. So let's talk about how to multiply matrices. So what is happening now is we are given the matrix A, which is 2, 2 minus 3, 4, 6, 2, 4, 1, 3, 5, 2, 1, 4. And we're also given the matrix B, which is 2 minus 1, 0, 3, 6, 6, 1, 4, 9. So given these two matrices, find first AB, then second BA. So we are given these two matrices and we want to multiply. So I'm going to do one example to demonstrate multiplication because one example will be just enough for the whole procedure. You see that? So now, how do we then deal with this? So to deal with this now, this is how we proceed. You see that? So we want to find A and B. So what we do is we write the two matrices next to each other that we are trying to multiply. So what is the matrix A? So it's 2 minus 3, 4, 6. And then also you have 2, 4, 1, 3. So we have 2, 4, 1, 3. Then also we have 5, 2, 1, 4. So we have 5, 2, 1, 4. Then we have also 2 minus 1, 0. Then we have 3, 6, 6. Then we have 1, 4, 9. Like that. So this is what we have. So now you want to multiply these two matrices. How do we go about that? So every time when they give you two matrices and they say multiply them, so one of the things that I will suggest, especially if you are new to this multiplication, first write down the orders of the matrices next to each other. You see that? So I'll write down the order of the first matrix. So what is the order of the first matrix? It's a 3 by 4 matrix. So we say 3 by 4. Then next to it, I write the order of the other matrix. And the other matrix is a 3 by 3 matrix. So every time what you do, every time when you are given two matrices and they say multiply, you write them next to each other, you write the orders. Then the next thing is the numbers that are immediately next to each other in the middle there, you just write down a box in them. You see that? So if these numbers inside the box are different, then multiplication is invalid. You see that? So if numbers inside the box are different, then multiplication is invalid. You see that? So when this is the case all the time, that you have these two things inside the box not being the same, then it's an invalid operation. So what we can then write is that AB is just pseudo or undefined. It's up to you. You see, like that. So we see now that these two matrices cannot be multiplied together. So now we have a pseudo solution or a non-existing solution. So what we're going to do now is we'll now go and try to find the other direction now. So BA, now let's try BA. So same thing, I write the matrices next to each other. So let me copy them. So I have 2 minus 1, 0, 3, 6, 6. Then I have 1, 4, 9. Then on the other side, I have 2 minus 3, 4, 6. Then I have 2, 4, 1, 3. Then I have 5, 2, 1, 4. So same thing that I did again, I'll come and write the orders of these matrices. So I have a 3 by 3 here. Then here I have a 3 by 4 here. So what I do, I put a box again in the middle. So now these numbers are the same. So if these two numbers are the same, then the multiplication is valid. But now, what about the outside things? You see? So this outside thing also, this tells you something else. You see that? So a combination of these gives the order of the resulting matrix. You see that? So it means if you are to perform this multiplication, the answer that you must get must be a 3 by 4 matrix. You see that? So that's the importance of these numbers on the outward. So your answer must be a 3 by 4 matrix. So now having that as an idea that you have to get a 3 by 4 matrix, now it's time to actually find the product. So now let's understand exactly how the product works. So I know that I have to have 3 rows. You see that? That's the idea. But now, how exactly does matrix multiplication work? You see that? So every time when you want to do matrix multiplication, this is how it works. So the first thing that you do is you go and look at your first matrix. And in your first matrix, you take the first row. You see that? Then what you do again, you go to your second matrix. And in your second matrix, you take the first column. You see that? So every time when you're multiplying two matrices, one thing that you should always know is that you always work rows. You always work with rows in the first matrix and with columns in the second matrix. So what you simply do is first I'll look at these highlighted rows and columns, and then how I proceed from here is I take the first number in my row and I multiply it with the first number in that column that is highlighted, which gives me 4. Then I move on to take the second number in the highlighted region and the second number in the column that is highlighted, and then I get -2. That -2 that I get, I add it to the previous result, which will give me 4 minus 2. And then I take the last number in that highlighted region and I multiply it and I get a 0. So everything is done like that. Then I proceed again following the same stance. So what I do now is I will keep my row in my first matrix, but I will shift to a new column in the second matrix. You see that? So now I shift to a new column in the second matrix. So I repeat the procedure. Now, the solution that I'm going to obtain here, since I'm holding here row number 1, it means the solution that I should get also must lie in row number 1. And since I'm fixing column 2, it means my answer also will lie in column 2, which means it's going to be at the top and coming next to what we have calculated. So I'll repeat the same procedure again, but now using that second column. So I'll take 2, which is my first number this side, to multiply that side, I get -6. Then I take -1, which is the second number that's on the row there, and multiply the second on the column, I get -4. Then I say 0, I get 0, like that. You see. Then after that, I still fix my row, but I move to a new column the other side. So I repeat the same thing. So I take 2 to multiply that, which gives me 8. Then I take -1, which gives me -1. I take 0, which gives me 0. Then as I've done, I shift to the last column. So 2 by 6, what do I get? I get 12. Then -1, I get -3. Then I get 0, like that. So now I'm done with the first row because I've been fixing this row whilst I was moving through the columns in the legs. So now what I'm going to do now is I'm going to change. So this side now, I'm going to shift to this row. But with this row, I'm going to move through all the columns in the second matrix. So let's go again. And so now I'm using the second column. So the answer that I'm writing also must lie in the second column. So I say 3 by 2 because I'm using the first column, the second matrix. I get 6. Then I say 6 by 2, I get 12. Then 6 by 5, I get 30. Then I'm done with the first column in the second matrix. I move to the next one. So I say 3 by 3, which gives me negative 9. 6 by 4, which gives me plus 24. Then 6 by 2, which gives me 12. Then again, I move on to the next one. So I say 3 by 4, which is 12. Then 6 by 1, which is 6. Then 6 by 1 again, which is 6. Then I move on to the last one. I say 3 by 6, which is 18. 6 by 3, which is 18 again. Then 6 by 4, which is 24. Then I'm done with this. I'm done with this row that I was using. So after I'm done with this row, I move on to a new one this time. So I move on now to this one. So moving to this one now, I'm gonna do the same procedure again without changing anything. So I say 1 by 2, which is 2. 4 by 2, which is 8. Then 9 plus 5, which is 45. Then I move on to the second column in the second matrix. Say 1 by minus 3, which gives me minus 3. Then I say 4 by 4, which gives me 16. Then I say 9 plus 2, which gives me 18. Then again, I move on to the second, to the third column that had a size. So I say 1 by 4, which gives me 4. Then 4 by 1, which gives me 4. Then 9 by 1, which gives me 9. Then I move on to the last part. So I want to say 1 plus 6, which gives me 6. Plus 4 by 3, which gives me 12. Plus 9 plus 4, which gives me 36. So the only thing that I'm left to do now is to simplify these. But without even wasting time on simplifying this, one thing that we can see for sure is that if you are to come now and check the things that we have been calculating, let's just try to highlight some things. You will see that we have 1, 2, 3, 4 columns, which is what we expect according to that red indicator there. We expect to have 4 columns in our final matrix. And if we come now and highlight the rows, you will see that for the rows, we have 1, 2, 3, which is exactly what we would want to get when we are performing this multiplication. You see. So yeah, this is how the multiplication of matrices work. So for now, this is all the preliminary material that you will have to know before we go on to the abstract part of linear algebra. So once you have a good understanding of all these things, now then it's time for you to get insight into this subject. But what you're going to see now in our next lesson is that our next lesson will be more like trying to redo everything that we have done, but in a more symbolic way, which is what we call abstraction. You see that? So it's good first to understand how to do things from a numerical perspective, so that when now we start moving on to abstraction, it is not something which gives you a hard time understanding what's going on here. You see? Otherwise, yeah, thank you for watching. We'll meet you on our next lesson. Bye.